Welcome to our continuing study of angular momentum. Back when we studied linear momentum, we looked at the concept of linear momentum conservation through the lens of collisions. Well, we can apply the concept of momentum conservation in a linear and rotational sense to some rotational collision problems. Let's get started. First of all, let's take a look at some practical examples of rotational collisions. Okay, on the left you see the clutch system in your car. Okay, now most of you probably drive automatics, and so you're not as familiar with this process, but if you do drive a manual, you'll know that you have to have a third pedal down underneath next to the brake pedal and the gas pedal, and that third pedal is the clutch. Okay, and what it does is it engages or disengages two spinning wheels, right? An example of a rotational collision. You'll see the flywheel, which is the engine part of the car. Okay, it's always spinning. Once the engine's running, the flywheel is always spinning. But you don't always want the wheels to be spinning, right? And that's the clutch, which leads to the transmission side. So depending on whether you have that clutch engaged or not, those wheels are locked together and spinning as one, or they're disengaged, and the engine can run, but the wheels aren't turning. You see another example in the middle here of someone jumping onto a merry-go-round. Okay, remember that a person or an object moving linearly can still be considered to have angular momentum about a point. So this person has angular momentum about the center of the merry-go-round, and we can look at this as a rotational collision. Thirdly, on the right, you see the rotational equivalent of the ballistic pendulum. Okay, in this case, for it to be like a ballistic pendulum, the object of mass m here, right, the ball, would have to hit this hanging beam and then stick to it and rise together. Okay, and it would be like a ballistic pendulum collision, except this time the beam is pivoting around its hinge there, right? It has some moment of inertia around that pivot. So these are some common examples that we have of rotational collisions. Let's take a closer look at one of these on the next screen. Okay, and basically what we've done here is the following. Okay, this is imagine you're looking down on its frictionless tabletop. Okay, so this is all happening horizontally. So coming from the left, we have an object of mass little m. Okay, it has a initial velocity, and it's going to strike a rod that's laying on the table initially at rest. Okay, mass capital M. I've indicated the center of mass with the dark dot. It's length L. Okay, and then we have the dotted line. That's so on the left here, right, we have before. Okay, and then here's the after. This is an example of a perfectly inelastic collision. So that ball, maybe it's a ball of putty, okay, it sticks to the beam or the rod, and they rotate together afterwards. And what we want to determine is what's the angular velocity of that rod ball system after the collision when the two stick together, right? Perfectly inelastic collision. This type of problem is quite challenging, and that's because of that little black X that you see on the rod. That black X represents the new center of mass of the rod putty ball system, right? Because when that ball attaches itself to the rod, we actually have a new center of mass. Okay, that shifts a little bit. I've exaggerated it here. We're going to call that distance x. Okay, notice, by the way, on the initial drawing we have the distance d, which is how far below the center of mass of the rod the ball impacts the rod. Okay, that's a distance d, and the distance x is going to represent how much the center of mass shifts from the center of mass of the rod, which we're assuming is uniform. So the center of mass is in the geometric center, right? In other words, this distance here, okay, is half L, okay. Same here, right? L over 2. But the new center of mass is below that. Okay, and that's what makes this problem challenging. We're going to throw all the tools that we have at this problem, okay, and that means linear momentum conservation, right? We're going to use linear momentum conservation, okay. We're going to use angular momentum conservation, okay. We're going to use the center of mass equation. Okay, remember you learned how to find the center of mass of a system of objects. And we have to use the parallel axis theorem, right? Because the rod now rotates around a new axis that's off the center of mass. Right? So we're going to have to throw all of these tools at this problem to arrive at our solution, which is omega. Let's go to the next page. Let's start with linear momentum conservation. Okay, it's going to look as follows. Obviously, before the collision, the only thing that's moving is the ball of putty, right? But afterwards, okay, they're going to be moving together. And I didn't point this out initially, but let me go back to the previous screen. That whole system, okay, is going to translate to the right. In other words, it's going to go like this, right? It's going to move to the right as well as spin to the right. Okay, it's going to move to the right as well as spin to the right, and it's going to move back to the next page at a velocity v prime, right? Or let's call it v final. Okay, v final. So there's your momentum conservation linearly. We can solve for the final velocity here in terms of the initial velocity, like so. All right, so there's our first expression. The next thing we want to do is we want to determine the center of that rod ball system. All right, so that looks like, all right, so our origin in this case is the center of the rod. That's why you see the m times 0. Okay, and we can solve this for the center and mass of the system, which is the x. Okay, I'm just going to call it x, but that in terms of how far away from the center of mass the ball impacts the rod, d, right? The distance d, it's going to be like that. So now we have two equations. Okay. The next thing we need to do is we need to determine the new moment of inertia of the rod putty ball system, because it's now rotating around a new axis that's not at the center of mass of the rod. So let me set that up. I'm going to call that new moment of inertia I sub x. Now we know, we can look up from the book, right? We know that the moment of inertia of a rod about its center is 1/12 ml squared. And in this case, right, the new center of mass is a distance x away from that geometric center of the rod. So this is what we're after. And what we're going to do here is we're going to substitute this x in right there. Okay? I'm going to spare you the algebra in the interest of time. So we've now applied our third equation to this system. I should clarify here. What this represents, okay, is not the moment of inertia of the whole system. It merely represents the moment of inertia of the rod after the collision around that new point, right? The total moment of inertia of the ball rod system, we're not there yet, right? We have to add the moment of inertia of the putty ball to the moment of inertia of the rod. And that's what we want to do next. So I'm going to go to the next screen for that. Let's see what I've written here. Okay, the new I, which I'm going to call I prime, okay, is the sum total of the moment of inertia of the rod around the new center of mass of the system, plus the moment of inertia of the putty around that point x. Okay, now hopefully you can see from the drawing here that the putty is a distance d minus x away, right, from the new rotational axis. Okay, so I'm going to pause again and write out that new expression, putting all this stuff together. Okay, in the brackets you see the moment of inertia of the rod, right, from the previous screen. Next to it you see the moment of inertia of the ball of putty, which we're treating as a point mass, right? Remember that the moment of inertia of a point mass is just mr squared, okay, where r in this case is d minus x. Now we just need to algebraically combine all of that. Okay, you see the solution for the new moment of inertia of the rod putty ball system. All right, this is rotational collisions, and yet we've made no mention yet of angular momentum. So let's take a look at that now. Okay, we're going to go to the next screen. And we're going to apply angular momentum conservation, okay, because it is also conserved, just like linearly it's conserved, it's also conserved rotationally. All right. So before the collision, all we have is the putty ball moving. Okay. Remember, it's moving in a line, but it's moving off the center. So with respect to the center of mass of the rod, okay, it has the momentum you see I've written here, angular momentum. And so that means that the final angular momentum must equal that as well. Okay. Now I'm going to substitute. Remember, we derived a value for x, right? So I'm going to put that in there. Okay, but that's from our center of mass. Our center of mass equation. Now you can see why I used the center of mass. Okay, so it's going to look like this. And with a little bit of algebra, we can reduce this to the following. Okay, again, an expression in terms of the given quantities. So here's the final angular momentum must be equal to that. All right. Now I'm going to invoke that other equation for angular momentum, okay, which is I omega. And now finally we get to where we want, which is we're trying to solve for omega. All right. So moving this around, you can see where this is going. Okay, divide both sides by I, where I is that new moment of inertia, right? The new moment of inertia of the ball of putty and rod sticking together. So what we need to do now is basically this needs to go here, okay, and then our gnarly expression from the previous screen for the I prime needs to go underneath. All right, so I'll pause and write that out. Okay, I have combined those two quantities into a monstrous fraction. And I have rewritten the I prime slightly. Okay, you'll see it looks like it has an extra m plus m term in it. I've just given those two terms of I prime, I've given them a common denominator, which you then see nicely cancels the denominator of. One more note, I've been a little sloppy with the v, the initial velocity, which I labeled in the beginning as v naught. So I've gone back on this screen. Notice I've put the v naughts in. Okay, so the v refers to the initial velocity of the ball. Finally, at long last, okay, doing some more simplification here and going to the next screen, we get an expression for our final answer, which is the angular velocity of the rod putty system. It's pretty ugly looking, but notice that it is all in terms of the given quantities. That's when we know we have a good solution, right, when it's all in terms of the given quantities. And there you see we brought the full arsenal, right, of our concepts to bear on this problem. I want to look at one more problem. We're not going to solve it, but I want us to look at how we might go about solving it. So you have some conceptual framework for doing this in class. Let's take a look at a very similar problem. Again, we have a ball of mass little m with initial velocity v naught impacting a rod of mass capital M at a certain distance from the rod center of mass, right, which we're going to mark as D. However, this time, instead of a perfectly inelastic collision where the two objects stick together afterwards, we're going to have an elastic collision. Okay, we're going to ask the following question. What does the distance D need to be so that after the collision, the ball comes to rest? The final velocity of the ball is 0. So again, we're looking at this from above. We're looking down on a frictionless table. It's all happening horizontally. And we're going to apply similar conditions as before, right? We're going to apply linear momentum conservation, right? Because this rod is going to be sliding across the table afterwards. But we're also going to apply angular momentum conservation because the rod is going to be rotating after the collision as well. And then finally, we're going to apply the definition of a elastic collision, and that is that the kinetic energy is conserved, right? In other words, notice that this rotational axis about which the rod is rotating is not changed, right? It's still the center of mass of the rod. So that actually makes this a little bit simpler than this previous problem because we don't have to mess with that I prime and the parallel axis thing. Okay, so let's look on the next screen and see how we might combine these. Okay, so here's kinetic energy conservation. Beforehand, we only have the ball moving. Afterwards, we have the rod rotating and the rod moving. Right? So what I'm going to add to this now is I'm going to add the angular momentum conservation. Okay, and I'm going to add the linear momentum conservation. Let's look at angular momentum conservation on the left. Okay, beforehand, right, we just have the angular momentum of an object moving in a straight line with respect to a point, which in this case is the center of mass of the rod, m v naught d. And then afterwards, we have I omega, right? Because remember that the ball has stopped moving, so it has no more angular momentum. Now the angular momentum is all the rod. And then I just simplify that and I get an expression for the angular velocity. If we look at this linearly, it's very simple. Beforehand, only the ball is moving, mv naught. Afterward, only the rod is moving, capital M, VF. And I get an expression for that. And you can see what's going on here. Now we're just going to take these expressions, right? This expression here is going to go right there. This expression here is going to go right there. All right? And I said that I would not work this out, and that's because you will. I will leave it to you to trudge through this algebra and arrive at a final expression for the letter D.